All right, let's dive in. Today, we're going to try and make sense of the wild, sometimes confusing world of cloud-native development. We're going to follow the journey all the way from building an app to keeping it safe when it's live. Let's start putting these pieces together. So, have you ever looked at the whole cloud-native landscape and just thought, wow, that is a lot? If you have, trust me, you are not alone. It really can feel like you're trying to solve a puzzle with, 1,000 tiny pieces.
I mean, you see all these logos and projects flying around. Kubernetes, Falco, KubeArmor, the list goes on and on. They're all super powerful on their own, for sure. But the real question is, how in the world do they all fit together? You know, where does one tool's job end and the next one's begin?
And that is exactly what we're going to do in this explainer. We're going to take all those scattered puzzle pieces and start putting them into a picture that actually makes sense, so you can see not just what they are, but how they all work together.
Okay, so where do all these puzzle pieces even come from? To really get that, we need to take a look at the organization that sits right at the very center of this whole ecosystem.
And that would be the Cloud Native Computing Foundation, or what everybody calls the CNCF. It was started back in 2015, and its whole reason for being is to bring some order to the chaos and, create a stable home for all this cloud-native software.
And at the very heart of this entire puzzle, there's one massive foundational piece, Kubernetes. Google originally created it and then donated it to the CNCF, and it basically became the game board where all the other pieces would eventually be played.
And from that one seed, man, the whole ecosystem just exploded. What's so wild about this is just how different all these tools are. You've got Kubernetes running the whole show, Prometheus watching over everything, Falco on security duty, Envoy handling the network traffic, and Helm making it easier to package it all up. Each one is a super specialized tool for a very specific job.
So all this variety, all these tools, they're all in service of this one big promise, of being cloud native, this idea that your apps can run anywhere. But turns out that simple little phrase is hiding a ton of complexity.
Yeah, when we say run anywhere, what are we actually talking about? Because it's not just one single problem. It's actually two totally separate challenges that pretty much every dev and ops team has to deal with.
So, first up, there's the hardware problem. How do you get your code to run on different kinds of computer chips, right? Like the standard AMD 64 processors and the ARM 64 chips that are becoming super popular. Then there's the environment problem. How do you deploy your app smoothly across AWS, Azure, Google Cloud, and maybe even your own private servers?
And to handle that second challenge, the environment one, companies usually go one of two ways. You've got hybrid cloud, which is kind of the best of both worlds. You keep your really sensitive stuff on your own servers, but use the public cloud for its power. And then you have a multi-cloud strategy, which is all about not putting all your eggs in one basket. You use services from AWS, Google, whoever, to get the best price and the best features.
So we've got two clear problems on the table, different hardware and different clouds. The good news is the cloud-native world has come up with some pretty clever solutions for both.
For that hardware problem, the answer is the multi-platform image. The easiest way to think about it is like a single, really smart container image. Instead of building one version for Intel chips and another for ARM chips, you build one image that has a kind of table of contents inside, a manifest list that points to the right version for whatever computer it ends up on. And the way this works is it's really elegant. You just run one single build command, and you tell it all the platforms you want to support. Docker then builds everything and creates that manifest list, which is basically a map pointing to the right image layers for each chip. So when a machine goes to pull the image, Docker just peeks at the local hardware and automatically grabs the correct version. So simple and so effective.
Now, when it comes to the cloud environment, the choice isn't quite as clear-cut. It's all about trade-offs. As you can see here, hybrid cloud gives you a ton of control, which is great for security and older systems, but wow, managing it can get complicated fast. Multi-cloud is fantastic for avoiding getting locked into one vendor and for finding the best prices, but trying to manage costs and security across all those different providers can be a real nightmare. So the key takeaway here is there's no magic bullet. It really depends on what you need.
Okay, so let's say you did it. You successfully built your multi-platform image. You've deployed it across your complex multi-cloud setup. Your app is live. But this is the exact moment a brand new and honestly a much scarier problem shows up.
See, just because your application is up and running smoothly everywhere doesn't mean it's safe. The whole deployment part is over, yeah, but the operational part, the runtime phase, is just getting started. And this is where the real security battle is actually fought.
And when you dig into runtime security,
you find that the entire field really just boils down to two completely different ways of thinking, two fundamental philosophies, and understanding the difference between them is absolutely critical.
The first one, and probably the more traditional way of thinking, is called detect and respond. And it's exactly what it sounds like. Its job is to spot something bad that has already happened and then react to it. It's all about what you do after the attack.
This diagram shows it perfectly. Look at step 1. A malicious command gets executed inside a container. It happens. The kernel sees this, as you see in step 2, and it generates an event that gets sent to some security tool in step 3. Then, finally, way over in step 4, that tool responds, usually by killing the process. But do you see the crucial part? There's a delay. The attack has already landed before it gets stopped.
And that delay, that little gap, that's where all the problems live. The malicious code always runs first. This opens the door for all sorts of clever attacks, like a time of check to time of use attack, where a hacker can swap a safe file with a malicious one in the split second between when the system checks it and when it actually uses it. And think about ransomware. A response that's even milliseconds too late is useless. The files are already encrypted. It's too late.
Which naturally brings us to the second philosophy, inline prevention. Instead of waiting for an attack to happen and then reacting, this whole model is about stopping the attack before it can even execute a single instruction. It's a preemptive game.
And this slide, wow, it just says it all. Look at that top diagram. That's an inline prevention tool. The attacker tries to run a bad command. The tool intercepts that request to the operating system, the syscall, before it gets processed, and just denies it, flat out. The attack is stopped cold. Now compare that to the reactive models you see below it. In both of those cases, the malicious command succeeds first. Only after it runs does something get alerted and the process gets killed. That might seem like a subtle difference, but in security, it is everything.
And all of this brings us to the final and most important question you should be asking about your own systems. Is your security strategy built around cleaning up a mess after an attacker has already gotten in, or is it about preventing them from ever making a mess in the first place? In other words, is your strategy reactive or is it proactive?